has next is interesting because it's not based off of whether or not we have anything left. Maybe. Could you implement so it's average and uses overreach method?
read about the curse that I want to enter. Let's give it a try. It seems to work really well on small projects.
Hey everyone, welcome back to Let's Write Some More Leetcode. Today let's solve the problem binary search tree iterator. We're basically implementing a class that represents an iterator over a binary search tree. It's supposed to be implemented by in-order traversal, basically what you would expect from a binary search tree if you've ever used, real iterator format or something like that. Because that's kind of one of the purposes of a binary search tree, to have the values in some kind of sorted order. It's not literally sorted, but it's in a way that you could iterate through them in sorted order pretty efficiently. There's really three methods we want to implement. One is just a constructor, and then two are the actual ones that have some functionality that we need to do. So one is the first would be the 3, then the 7, then the 9, then the 15, then the 20, then it would be done. After all 5 values, the has next should return false, because there aren't any values left for us to return. But while there are still values though, then we're going to return true. But we're not actually returning the value itself with the has next function. The next function though is the one where we're going to be returning the value. So the kind of trivial solution to this that you might be thinking of, why not just implement in-order traversal, run it on the tree, have every single value put inside of an array, and then we can just maintain like a single pointer, right? Start at the first value, return this, etc., right? Until we're done with the array, and then we're good. Before we implement this solution, let's understand how efficient it would be. Well, overall time complexity is pretty good. O of n, we're just iterating over the entire array, or not the array, the tree, and I guess we can put that in the constructor if we want to. So the constructor will be O of n time. Not bad. And then each has next and the next function, each of those can just be done in big O one time, because we're just incrementing a single pointer over this array. Now the memory complexity is also clearly going to be big O of n, because we're putting every single node in an array. And if I showed you kind of the bottom part of this problem, they ask us, can we do better? Can we actually implement a solution where the memory is not the size of the tree?
What's up, Chucky? Just doing Leetcode. Interesting, so I could technically just initialize an array then. That's a naive solution. Mega DFS for this node. I can reduce, you know what, I'll just I'll have it like early on. Alright, should be better now. What's up, Hilo? Yeah, unfortunately had another headache right before I started this stream, so I'm just avoiding any blue light. Studying gets me nervous and stressed. That's rough to hear. If no dot left, then do we not just traverse through the left? And then if no dot right, I think we would also. So if we have no dot left and no dot right, then we're going to left and right. However, if we stop at this position, we can self dot in order dot appends no dot file. I think we can print in order self dot in order. I think. To see what we get. I don't think. I just put some returns. Biting my fingers when you study. That's tough, I guess. 3, 7, 9, 15, 20. Yeah, this actually works. And then, yeah, we'd have a pointer. Okay, this makes sense. So this is in order. Thank you, Hilo. Appreciate you.
But the memory is actually big O of h, where h is the height of the tree. And can we make it?
Have any nervous habits? I don't know. I just do it, I guess. I don't know if I can relate, to be honest. I just do it.
So that has next and next don't necessarily.
I don't know. I guess in my head, it's like, what am I gonna do? Just not study and just don't do anything. I don't know.
Have a big O of 1 time complexity, but they have an average time complexity that's constant. Meaning if we ran the has next and the next function for every single node in the tree, what would have been the average time complexity? It would have to be big O of 1. So that's kind of the restriction. So you can see that it's kind of a trade-off. We're getting better memory complexity and slightly worse time complexity because this is no longer big O, this is the average. So how would we go about implementing this kind of more efficient solution? Has of the tree, discuss, can we do better? Can we actually implement a solution where the memory is not the size of the tree, but the memory is actually big O of h, where h is the height of the tree? And can we make it so that has next and next don't necessarily have a big O of 1 time complexity, but they have an average time complexity that's constant. Meaning if we ran the has next and the next function for every single node in the tree, what would have been the average time complexity? It would have to be big O of 1. So that's kind of the restriction. So you can see that it's kind of a trade-off. We're getting better memory complexity and slightly worse time complexity because this is no longer big O, this is the average. So how would we go about implementing this kind of more efficient solution? Well, I'll tell you how, but first let me just tell you a couple problem solving techniques that you can use if you were stuck on this. First of all, this is a tree problem clearly. And usually the solution to tree problems is always going to be some tree traversal, whether it's, you know, a DFS or a BFS. And of course, these methods can be implemented, DFS can be implemented recursively, and it can also be implemented iteratively. So that's really your options here. You have to try to see which kind of solution will be somewhat effective on this problem.
I mean, anytime we want a height of a tree, I feel like that's BFS. That would be my thought.
And if none of these are effective, then there might be some kind of special algorithm that might be needed to solve this problem. Probably an algorithm you wouldn't be able to figure out by yourself, to be honest. In that case, you would need a hint from your interviewer. But the good thing is we don't need a special algorithm. We can do this with a regular in-order traversal. But first, let's try the recursive traversal and then understand why that's not going to work. And then I'll show you why the iterative traversal is going to work. So let's say we're doing it recursively.
Recursive doesn't work?
We start at the root. We try to go left as much as we can because we're trying to do this in order. So, you know, we visit here, then we visit here, and then we keep going left until we reach here, which is null. So then we're going to pop back up here and say, okay, this is the return value. So for the next, this is what we would return. But how can we do that if, you know, we're 2 functions deep? Because we did this recursively. We can't just return from the next function. We have to pop back to the root, which is okay because let's say we just decide to record these in some kind of list or some kind of array data structure. That would work. But at that point, you're kind of doing extra work. While this is probably feasible, what we're noticing is we already have these in memory because we're doing this with recursion. And
imagine being able to build an app with your name on it just by thinking about it. Meet Base 44, a complete AI creation platform.
then we're just adding it to a list. We can maybe just skip the recursion anyway and just initially add these values to a list. So instead of even doing this recursively, let's do it iteratively and just start adding the values to a list, or rather a stack, which is used for iterative DFS. So this does satisfy the overall memory complexity of big O of H, because any in-order traversal, whether it's recursive or iterative, is going to have big O of H memory. But the thing here is we're not adding every single value to the stack. We're only adding up to the height. And by the way, if you're not familiar with iterative DFS, I actually did a video on it a few days ago, so I recommend checking that out if you're not too familiar with it. But basically, this is how it's going to work. We're going to...
Maybe I should just watch that video just because... I think it'd be good. What was that video?
And by the way, if you're not familiar with iterative DFS, I actually did a video on it.
Iterative and recursive. Alright. How you doing, Lapis? Hope you're doing good. Iterative and recursive DFS. Leetcode. Okay.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve binary tree in order traversal. And this is actually a pretty trivial problem if you've done anything with trees before, especially if we do the recursive solution, which we will. But we're going to take that recursive solution and also figure out how we can make an iterative solution doing that. Now, even though the code of the iterative solution is going to be completely different from the recursive one, the concepts are actually the same. Like what's going on under the hood is pretty much exactly the same, so that's what we're going to use to actually figure out this more difficult solution. So simple enough, we're given the root of a binary tree, and we want to return the in-order traversal of the values of all of its nodes. So in this case, for this tree, this is the root. We're going to do an in-order traversal. How do we do that? Well, we start at the root. We don't actually process the value just yet. First, we want to do the entire left subtree, but it doesn't have a left subtree, so we don't have to do anything. And next, we take the value 1 itself and add it to the result. So here we have a result, and 1 is added to it. Now we don't have to visit this node again. But now we're going to run the exact same algorithm recursively in order traversal on this right subtree. So we pretty much do what we did before. Before we visit this node itself, we have to go through its entire left subtree, which is pretty small in this case. It's just a single node. This is kind of the base case because now we have to go to the left subtree of this node, but it doesn't actually have a left subtree. Nothing's there. So then we can process the value 3. We can add 3 to our result, and then we're done with this node. Then we would go to the right subtree, but it doesn't even have a right subtree. So now we're done. We go back up to our parent node, and now from this node's perspective, since we just went through the entire left subtree, now it's time to process this node. The value is 2. We add that to our result, and then we would go to the right subtree, but it doesn't have one. So we're pretty much done in this case. That's the entire result. 1, 3, 2. You can see it's the same as what they expected. Overall time complexity of this algorithm doing it recursively is big O of n because we do have to visit every single node in the tree. The memory complexity in the worst case is also big O of n because of the function call stack. Because if we do implement it recursively, we have to put the parent nodes on the stack before we can actually pop back up to them. We'll actually go in more detail onto like what the stack is when we actually do the iterative solution. But now let's really quickly just write up the code for the recursive solution. Okay, so just coding up the recursive solution real quick. We are going to create a nested function actually because as we go through the function, we want to be building our results. So I'm going to call the nested function just something simple like in order. It's going to take in some node just like this function is. But this variable result out there is also going to be accessible from within this function because this function is defined inside of the outer function. So this is kind of like a global variable for the purposes of this function. It'll just make things a little bit easier. But for the actual in order traversal, we know it's a recursive algorithm. Recursive algorithms have 2 parts. The base case, which in this case is pretty simple. If a root is null, right, not root, so if the root doesn't exist, then we can just return. We're not going to need to do anything. But if the root is not null, that's when we do the in-order traversal. And we know in-order traversal is pretty simple. First, we go through the left subtree, whether it exists or not. We can pass in the left subtree by taking root.left into the in-order function. And then once that's done, it's time to process the root node itself. By doing that, we're just saying result. We're going to append the value of the root node to the result. It's just that simple.
If
We
not,
multi-service and multi-signal investigations through our stock investigation workbench. Our analysts are actively
And after we do that, we're just saying result. We're going to append the value.
what's up, Moku? Yeah, have to do the flux today. Can't risk any headaches.
Left subtree by taking root.left into the in-order function. And then once that's done, it's time to process the root node. That's when we do we know it's a recursive algorithm. Recursive algorithms have 2 parts. The base case, which in this case is pretty simple. If root is a null, right, not root. So if the root doesn't exist, then we can just return. We're not going to need to do anything. But if the root is not null, that's when we do the in-order traversal. And we know in-order traversal is pretty simple. First, we go through the left subtree, whether it exists or not. We can pass in the left subtree by taking root.left into
Our base case is if not root, return.
the in-order function. And then once that's done, it's time to process the root node itself. By doing that, we're just saying result, we're going to append the value of the root node to the result. It's just that simple. And after we do that, the last thing we have to do is pretty much do the exact same recursive algorithm on our right subtree. So whoops, let's copy and paste that and just change root.left to root.right. So I'm going to leave it at that. So we created our in-order traversal. It's very simple. We have a global variable, which is the thing that's being updated from this function. So let's make sure to call our in-order traversal, passing in the root node that was passed into the outer function. Once that's called, our result should be updated. So then we can go ahead and just return our result, and that's the entire recursive algorithm. So I ran the code and it does work. So now let's get into a more difficult solution. Okay, so now let's actually get into the iterative solution. And we're actually going to look at a different example to get a better picture of what's going on under the hood. And so this is going to be our function call stack, but I'm definitely going to simplify it a lot because in a real call stack, a bunch of things are pushed onto the stack, like the function, a bunch of variables, the local variables, the line that we were at executing the code, and things like that. Because when you call a function from inside a function, it has to remember to get back to the original function. That's what the stack is for. So we called the function once, then we called the function twice, and then let's say the exact same function. After we finish the second call, then we have to go back to the first call. That's how recursion works. But I'm going to oversimplify it a lot, and I'm actually just going to use the node values on our stack just to kind of simplify things. But so this is how it would work in a regular recursive in-order traversal for this. First, we take this node. We don't want to add this to our result just yet. We want to push this to our stack for the time being. So we're going to put 1 on the stack. That's the node 1 that we're talking about. And we want to now traverse the left tree before we traverse this node. But we're putting it on our stack to remember that we.
That's why the memory is the height of the tree. Because the stack will only be as big as the height. Because we're going to pop from it anytime we need to get out of it. The longest path, I guess.
We do have to do this eventually. So next we go to node 2. We're not going to process this node either. We're going to push this onto our stack. So node 2 is also on our stack. Our result is still empty. Then we go to node 3 because we're going to the left subtree of 2. Now 3 is also going to be pushed to the stack. And then we're going to go visit the left subtree of 3. It doesn't have anything though. So now is the part where we would pop from our stack. So we're going to pop 3 and add it to our result. So let's also cross it out here. Recursively, this would have been left subtree of 3. It doesn't have anything though. So now is the part where we would pop from our stack. So we're going to pop 3 and add it to our result. So let's also cross it out here. Recursively, this would have been a function call, and we would see, okay, this is null. So then we'd pop back up to our parent 3. Now that we popped up to 3, we're going to check if it has any right children, because as you're noticing now, even recursively, what this does is we go left, we go left, we go left until we can't go left anymore. Then we pop back up to our parent, and then we go right and see if anything's there. At this point, nothing is in the right subtree, so we don't do anything here either. But we are going to now pop again from our stack, because what we're saying is we did this entire subtree, and now we can finally go up and process 2. So we pop from the stack again. 2 is added to the result. We can cross 2 out over here again, and now similarly, when whenever we pop up to a node, we want to then check its right child if it has any. Right now we do. So now we're going to run in order traversal on this 4. Notice how though, when we do go right, we don't put anything on our stack, because once we're done with this subtree over here, we're going to pop 1 from our call stack, because as you can see in the picture, we've processed everything except 1. So now we're going to go to this 4 node, and 4 would basically be pushed to the call
That wording was so confusing.
stack, and then we'd go left, nothing is left.
Oh, he says we don't pop 1. Yes, that's correct, because we're not done yet. Yeah, we're still in the left subtree.
So that means we can actually pop 4 from the call stack as well, put it onto the result, cross this out. We would check if there's anything on the right side. Of course, there isn't. So then we can go back up and pop again from our call stack. Now we're going to pop 1 from the call stack. So we're back up here. We can cross this out, add 1 to our result. And then we would go to the right subtree of 1, which is 5. Now, in reality, we would put 5 on our call stack, check left, nothing is left. So then we'd pop 5 from the call stack, add it to the result. And then we would try to go right from 5. It doesn't have any right children. So we're pretty much done at that point because our stack is empty and we don't have any current node. So that was basically a simulation of what's actually happening under the hood with a stack. And you can also kind of see why the stack in the worst case is going to be big O of n memory, because in the worst case, we could have everything pushed onto the stack all at once. What an example tree for that would look like is basically if the tree just happened to be like a linked list.
That is true. If the tree was just the size of... there was only one path of the tree, then in that case the stack would still be O of n. But in most cases, I don't think trees are built like that. So if a tree is not built like that, then we can safely assume that the height of the tree is usually the average case for most height, like most tree memory complexity wise.
Maybe it only had left children, right? Something like, right, if a tree looked like this, then we would end up having to put all values on the call stack. Okay, but what you might not realize is the simulation that we just did is exactly how the iterative solution works as well. But instead of having the function call stack take care of things for us, we're actually going to manually update our stack and do things iteratively. It's basically going to be the exact same. I'll do a very quick simulation just to give you an idea. So instead of doing this recursively, we're going to have a pointer. So right now our current pointer is going to be at 1. And what the algorithm at this point is going to do is we're going to keep going left until we can't go left anymore. So what we're going to say right now is that, okay, this node is non-null. Let's put it on the stack. So the node 1 is going to be added to the stack. Now our pointer is going to go left. This is also not null. So let's add this to the stack. 2 is added to the stack. Now we get to 3. 3 is also not null. Let's add it to the stack. And then we go to the left child of 3, which is null. It doesn't exist. So at that point we pop from the stack. We pop 3, we add 3 to the result, and let's just cross it out in the picture. We would try to go to the right child of 3. But again, we see it's null, so then we pop from the stack again. So now we get to 2, we can cross it out, we can add it to the result. We try to go to the right child. Right after we pop a node, we go to its right child. So 4, in this case, it does exist. Okay, it's not. So that's where our pointer right now would be, by the way. Our current pointer would be here. Since it's not null, we add it to the stack, and then we try to go left. It doesn't have any left child. Again, we pop from the stack 4 and then add it to the result. Let's cross it out here as well. And every time after we pop a node, we try to check its right child and then run the same algorithm there. It doesn't have a right child though. So now once again, we pop from our stack.
It's a Bayush.
We pop 1, add it to the result. Now our current pointer is up here at this 1. So let's cross it out and then try to go to the right child down over here, which does exist. So now we would take this value 5 and add it to the stack. Let's just add it here because we're out of room. And then we try to go to its left child. It doesn't have one. So then again, we pop from the stack, pop 5, add it to the result, and then cross it out here. Now our current pointer would try to go right, but there's nothing there. It's null. So at that point, we know we're done because our current pointer is at null. It's not pointing at anything. And our stack is empty because we would try to pop from our stack now, but there's nothing there. So at that point, we have no nodes left. We visited everything. We built our result and we can return it. So conceptually, this is very similar to the recursive solution. The code is going to look a bit different though, but you can kind of get an idea of it's going to be some while loops going left and stuff like that. Okay, so now let's code it up. Okay, so this is the recursive solution. I guess I'll just leave it here if you want to take a look at it. The only thing we're going to need from here is the result. We're also going to need a stack. So let's get an empty list for our stack. And our current pointer is initially going to be pointing at the root. We want to continue this algorithm, the iterative in order traversal.
So while
our current pointer is non-null and our stack is non-empty. So basically, if either of these are non-empty, so if our
current pointer is non-empty or
current pointer is pointing at a real node or our stack is non-empty, we're going to continue this algorithm. What we want to do is just go left as long as we can. So if our current node is not null, we're going to add it to the stack. So stack.append the current node and then move our current pointer down to the left. And we're going to keep doing this as long as it's possible. Once this loop exits, that must mean current is pointing at null. So what we should do now is pop from the stack. So stack.pop and our current pointer should now be pointing at this node that we just popped. Let's append this to our result just like we did in the drawing. And remember, whenever we pop a node, we append it to the result and then we shift to the right. So now our current pointer is going to be shifted to the right node. And what do we do to the right node after we've shifted there? Well, we just run our regular in order traversal. So what should I write here for the code to simulate a regular in order traversal? Well, didn't we just do that right now? Isn't this whole thing a in order traversal?
It does another while cur. Does that make sense? I don't know if that makes sense.
So what would happen if we didn't put anything here? Well, we're going to go back up to the loop. We're going to see that our current pointer is non-null, or at least our stack should be non-empty. And if that is the case, then we're going to get back into this loop, right? For that node that we just shifted down to the right, we're going to try going left as far as we can, which makes sense because that's what we do with any node. But if that node is null, then this loop is not even going to execute. So then we would end up just popping again from our stack and then appending that to the result and then doing it all over again. So as you can see, even though this code looks a lot different from this one, they are doing the exact same thing with a stack. Maybe I made it look easy, but this code is pretty tricky to come up with on your first time if you've never done an in-order iterative solution before. But that is the entire code. So now let's return the result and run the code to make sure that it works. Oops, I was stupid again. We're not appending the current node itself to the result. We're appending the value. So I always make that mistake, but now let's run once what an example tree for that would look.
Oh no.
When your kid is hurting and there's nothing you can do about it.
Look like is basically if the tree just happened left, and we're going to keep pointer as we can.
Okay, so the thing is, like, I don't know if it's that intuitive to do another while loop.
So basically, if either of these are non-empty, so if our current pointer is pointing at a real node or our stack is non-empty, we're going to continue this algorithm. What we want to do is just go left as long as we can. So if our current node is not null, we're going to add it to the stack, so stack.append the current node, and then move our current pointer down to the left. And we're going to keep doing this as long as it's possible. Once this loop
I guess so.
exits, that must mean current is pointing at null. So what we should do now is pop from the stack, so stack.pop, and our current pointer should now be pointing at this node that we just popped. Let's append this to our result, just like we did in the drawing, and
And then now we move the current pointer to the popped value. I gotta visualize this. I feel like recursion is always difficult. Recursion is always difficult. Where is... I don't think I have another Excalibur. Yeah, I think I lost Excalibur. Alright, so let's just quickly draw some stuff. So let's say we have a simple example, right? Let's kind of zoom out of this a little bit. Got this one goes like this to 2 and this to 3. Why is the screen yellow? Because I'm trying to keep myself safe. That's why. Huh. So we stack append cur.val, go left, and then I guess, oh, I see, because we go actually to the point, so I think we technically stop at this node, which is a none, right? So then we say cur is back to this element, which it's not crazy intuitive if you've never seen it before. And then at that point, cur stack pop, because our current stack is set to give myself some more space. The current stack is set to 1, 2, right? We pop 2 out and we append it to res 2. We're done with this. Then we process right. And it's interesting how you don't have to do a while loop for the right, just the left.
Remember, whenever we pop a node, we append it to the result, and then we shift to the right. So now our current pointer is going to be shifted to the right node. And what do we do to the right node after we've shifted there? Well, we just run our regular in-order traversal. So what should I write here for the code to simulate a regular in-order traversal? Well, didn't we just do that right now? Isn't this whole thing a in-order traversal? So what would happen if we didn't put anything here? Well, we're going to go back up to the loop. We're going to see that our current pointer is non-null, or at least our stack should be non-empty. And if that is the case, then we're going to get back into this loop, right? For that node that we just shifted
That's true. We should say it's normal.
down to the right, we're going to try going left as far as we can, which makes sense, because that's what we do with any node. But if that node is null, then this loop is not even going to execute. So then we would end up just popping again from our stack, and then appending that to the result, and then doing it all over again. So as you can see, even though this code looks a lot different from this one, they are doing the exact same thing with a stack. Maybe I made it look easy, but this code is pretty tricky to come up with on your first time if you've never done
I agree. It's not easy to come up with that if you've never seen it or done it before.
an in-order iterative solution before. But that is the entire code. So now let's return the result and run the code to make sure that it works. Oops, I was stupid again. We're not appending the current node itself to the
Okay, I mean, this makes sense so far. Let's go back to the original question, right? This
a few days ago, so I recommend checking that out if you're not too familiar with it. But basically, this is how it's going to work. We're going to add these two values to our stack. Basically, we're adding as many values as we can. So let's say our stack looks something like this. And then if we called the next function, we would just go ahead and pop the value and then return the 3. But what's going to happen after we pop that 3 value? Should we do anything different in that case? Because what if we actually had a right child of this 3? We know for sure it doesn't have any left children, because if they did, we would have either popped them already or they would be on the stack right now. So 3 doesn't have any left children, but it could have some right children. So what we're going to do after we pop that is check. Does it have a right child? It doesn't in this case. But if it did have a right child, we would take that right child, add it to the stack, and then basically do what we did when we originally started at the 7. From that node, just go as far left as we can, adding each of the nodes to the stack. That's how in-order iterative DFS works. In this case, we don't though. By the way, what if we called our has next right now? Would we return true or false? Well, since our stack is non-empty, we know for sure that we do have some nodes left. But is that the only criteria? We'll have to revisit to confirm that we can just check if our stack is non-empty to return true for the has next.
We can check if the stack exists or not at any point in time. That makes sense.
100% sure about that yet, so we'll have to revisit. So now if we call next again, we're just going to pop 7. And similarly, from 7 now, we're going to go to the right child. In this case, it does have a right child, 15. So we add 15 to the stack, and then we go.
Yeah, you got
How many adds?
Go as far left as we can. So we go to the 9, add 9 to the stack. We go to the left child of 9, but it doesn't have one, so then we know we can stop. So notice how we still have a 20 left. It hasn't yet been added to the stack, and it won't be added to the stack until we have popped these values. That is to ensure, first of all, that's just how iterative DFS works in general, but that is also to ensure that we stay within the O of H height of the memory limit. So now, literally the only
That's right. That's how you stay in the O of H. Yep.
thing we can do is either call has next, which is going to return true because we know for sure we have some values left in our stack. And we also call next a couple times, so we're going to pop this 9. It doesn't have any right children, so we don't do anything with it. We can also pop this 15. It does have a right child in this case, so now we're going to go ahead and add 20 to the stack. And then from 20, we're going to try to go as far left as we can, but it doesn't have any left children. So at this point, we've pretty much solved the problem, right? We're going to call next again. We're just going to pop the 20. Then we look, does the 20 have any right children? No, it doesn't. So at that point, the stack would be empty, and we're pretty much done. So the question we had left was, how are we going to implement this has next? Can we just check if the stack is non-empty to return true? Yes, we can, because notice how before we return any of the values, we have to add them to the stack. Even if we just had a node with a single value, we'd have to add it to the stack before we returned it. Suppose we had a tree like this, we'd add all of these to the stack, and then as we call the next, we pop them one by one until the stack is empty, and that's how you know that we're done. Now, what if the tree had some more nodes like this? Well, in that case, we do the same thing, pop until we can't pop anymore, but as soon as we pop to this one, our stack would become empty. But then as soon as that happened, we would end up adding these values, well, not both of them, I think we just add this one to the stack, so our stack would still be non-empty.
Am I saying something? I am. You can't hear me? Why are you learning this? I'm just learning it because I have an interview to study for. That's why I'm learning it. This is just like the coding SATs, really.
And then we pop that and then add this one to the stack. So as long as our stack is non-empty, we still have some nodes that we need to traverse. Okay, so now let's code it up. And so the way I'm going to call our initializer, our constructor, is basically by initializing the stack. And since we're going to have to remember the state of the stack in between next calls, we should make the stack a class variable. It should be a part of the object. And we should also initialize
Yes, I agree.
the stack in the constructor, because we could be given a non-empty tree as a parameter in the constructor. And if we don't initialize our stack, then if we call has next, it's going to return false, even though we do have some nodes left. So let's initialize.
Maybe I should try answering this question now that I know all the information that I just got. So that's interesting. I didn't know this before, which is good that I didn't spend that much time trying to figure out the solution. I think if at any point, I guess if there is ever a question on whether or not the height of the tree is the limitation on the space complexity, then we have to consider iterative DFS instead of recursive, because iterative DFS incorporates a stack, right? And this is technically, I guess, better than a recursive DFS, because DFS by default will incorporate a function stack call, which is O of n size. If your code runs, you'll be declared hot. Yeah, I guess so. What I have the filter on? It's because I had a headache, so I'm not trying to get it again. And when I get headaches, I get more sensitive to bright lights. So unfortunately, I am not normally functioning human being. Didn't know that? That's fine. I don't expect people that are not, in this field to know. Thank you, Seraphic. I appreciate you. I wish you the best in life as well. So self.s will initialize as the stack. And we'll go. That's the thing. I don't think we just need to have the current pointer. I think we initialize everything. So we need to create a DFS function, do we not?
Our stack, and we're going to do it very easily while the root is.
Oh, that's right. And of course, we're going to have to do this not recursively. So while root and or self.s. So in this case, we said we're going to do another while loop, right? So while root.left, we're going to keep going until there's elements in the root.left. Although, do we not want to create a cur variable to say so that we don't lose position of root? I don't know. I don't know what's politically correct. Let's find out.
It's not null. We're going to add that node to the stack and then just update the pointer that root is pointing at and just set it to be root.left. left. Maybe to make this more clear, I could have used like a cur variable. I could have said cur is equal to root and then have updated that cur variable. I guess it just saves one line of code. So as long as it's not too confusing to you, I think this is fine to do. It's not like we're actually modifying the tree or anything. Now for the has
That's true, I guess.
next function, which we know is pretty easy. As long as the stack is non-empty, then we can return true.
Wait, so this guy, all he does is, while we have a root, why doesn't he check, interesting, okay. That's interesting. While roots, all we're doing is we're going to root is equal to root dot left. Oh, but we have to self.s.append root dot val, and then root dot left. Is that the order? Yeah, I guess so. That is the order in which we do things. Yeah. So in this logic, all we're doing is we're saying we want to start at the root, and we want to append to our stack 7, then 3, and we keep going left until we can. And then in that case, if we have a next call, we have, what do you guys study, by the way? What are you guys doing right now? Where are you guys at in life? Are you guys still in school? So working? Nice. Good stuff. What do you do for work? Hotel management. Oh. I've heard some people in that field can make a lot of money. Is that true? All right. So we also got, okay, so we got this function basically set up for us. So the next would basically mean we basically just pop, right? We can simply just pop out of it, I think. Returns the number at the pointer, right? So self.s.pop, just the cur node, and we can return cur node.val. And the thing is, like, even though we pop, we're going to need to traverse through. I feel like, I think we need to do more. I was just scrolling through YouTube and this channel got recommendation, so I just clicked. Yeah, I don't know how the YouTube algorithms work, but it's definitely a mystery to me sometimes.
True. If it's empty, we can return false. Okay, now for the next function. What? No.
If it has next, that's easy because we can simply just return stack. If we have self.s, return true. If self.s, else false. Today I started Leetcode. Hey, good stuff. Everyone starts somewhere, and that's honestly one of the hardest things to do, I feel like. So, congrats, man. I wish you the best of luck. I'm having a terrible headache. Oh, I mean, I can relate. I literally just had I don't know if you guys know anything about cluster headaches, but I just had a cluster headache. I don't know if you call it an episode or an attack, but I just had one right before I started streaming. So that's why I'm kind of low energy, because whenever I have those like attacks, it's mentally exhausting. How do I have the filter? It's just called Flux. You can just type in Google Flux and just download this software. It's free. It's really great. Helps you to sleep better at night since it reduces blue light. Yeah, I'm doing okay. I think I'll be fine. I think I will be just fine. Hopefully. Biggest regret was procrastination. It's okay. There's always tomorrow, and as long as you're doing the most you can, that's all you can really do, right? That's all you can really do.
Node are we going to return? Well, basically whatever's on the top of the stack. And by the
Self.stack. Okay, that's a better way to say it, right? Return self.s not equal to this. Yeah, because this is true then, right? As next. Otherwise, if there's nothing left, which means it would hit the else case of this, which means, yeah, it's clever.
By the way, they tell us that next is...
What's up, Sat Yanj? Just got done with study. Have a good dinner. I appreciate you. Cluster headaches, one of the most painful things. Yeah. I feel like my pain tolerance is usually pretty high. I usually don't feel that. I feel like I can, suck up pain pretty well, but stuff like this, it's different. I don't think anyone can truly understand what somebody with this has unless you've gone through it yourself. It's rough. I can't lie. Literally this past week, I was in a state of why me? Why me? Of all people, why did it have to be me? But it is what it is. You live and you learn. Is there any option to turn it off? Yeah, you could always turn off Flux. You can just press Alt and to turn it off at any time. You can also control the intensity of the filter, so it's very flexible.
If it's valid. So basically, if there still are nodes left, then next is going to be called. So we know for sure that our stack is not empty. So we're going to go ahead and pop from the stack, and we're going to get that node. And when we're returning, we're going to return the value of that node. But before we do that, we know that there's a little bit of work left for us to do. That node that we pop could have some...
Yes.
Could have a right child. So let's get that.
Yes. Okay. So I was right about this. In the case that we do pop something, and there is something on the right side, right? So that's the thing. We do put it in a while loop, I guess. While kernel.right. Is it while kernel.right?
That right child. It could be null though. So let's have a loop while the current pointer is non-null. We're going to go ahead and add that to our stack, and we're going to go ahead and update that current pointer to be cur.left. We're going to keep going left as far as we can, adding each.
Biggest regret? I think biggest regret for me was I don't know. I try not to live life with regret, but if there was one thing I could have changed in my past, I think I would have liked to have been... I think I was babied too much as a kid, but I feel like those are things outside of my control. I feel like there's really not too much I feel like I can say that I regret. I always take those and, you know, use it as something to just better myself in the future. And choosing comp science, you know, yeah, I did choose, you know, I do wish I studied all this stuff earlier. That's one thing I wish I did, but again, everything's like, you could always have done more in the past, but what's more important is what you're doing right now, because that's all you can control, right? So, okay, we're gonna say cur is equal to cur node dot right, while cur self dot s dot append cur, and again we're gonna do the same thing. We're gonna keep moving left. So this way we will keep going left whenever we can. So in this case, we actually popped this one, and in the cur is equal to cur dot right, there's nothing here, so we don't do anything. Which is fine, because then we just popped from the stack again. So cur node is now at 7. And then we say cur is equal to cur node dot right, and while cur, we will keep going left, which actually works. There is no such thing as cur node dot right. Okay. You guys are really chill, by the way. I usually don't get too many viewers when I'm studying, but I'll say you guys are very chill. Not you, Techno. No, you're chill, Techno. You're chill. Everyone's chill. Oh, we stored the root.val, which is actually incorrect. That's right. Okay, that makes sense. Yeah, that makes sense.
Node to the stack. Notice how that's pretty much exactly what we did in the constructor. So if you really want to, you can create like a helper function for these 3 lines of code so you don't have to, rewrite them. I'm not gonna do that though, because I'm pretty lazy. I don't think it's a huge deal if you repeat yourself and it's just 3 lines of code. So I'm gonna run this as is. Hopefully we implemented it correctly. And as you can see on the left, yes we did. It's very efficient. So I really hope that this was helpful.
This question I don't think I would have been able to figure out on my own, I can't lie. Alright. Why don't we just start again from scratch, I guess, just to make sure that I truly understand what's happening. So like we said, if we want something O of H space, we have to iteratively... Where do you guys live, by the way? Where are you guys from? I'm sure you guys are everywhere in the world. You have to iteratively go through. DFS with a call stack, with a stack. SoCal. Can I turn off the filter? No, I can't. I can't. I actually can't. I had a cluster headache right before this stream, so yeah, I'm sensitive. I know I meme about it, but like the reason, part of the reason why I like being in darkness is because bright lights usually trigger my cluster headaches, or they don't really make it better. But yeah, when I have them, I just want to be in like very calm and not white light, like bright lights. It's too much. Austria, nice. Austria, that's cool. I always thought people with Australian accents were. I like the Australian accent. It sounds very pleasing to the ear. Wait, but is Austria the same as Australia? Or am I dumb? I always sucked at geography. Self dot s to an empty stack, and we can just go through this while root. Oh, they're different countries. I guess I was kind of far off. I guess I was quite wrong. Yeah, people get confused. I don't know. I've never been good at geography. I'm very bad at it. Soft light is nice, yeah. It helps me feel less. It feels warm, and more inviting. O2 therapy, I mean, I definitely have thought about it. O2 therapy, me being the cheap ass that I am, which maybe I shouldn't, given the fact of how severe they are. I think I've like tried to do a little research on like how much it would be, and I think it would cost like each time I do it, I think would basically be $100. So like I think I could probably get like maybe a tank that would last for like 10 sessions, but that would be like $1,000, which that's why I've always looked for solutions that were just way better financially. I think from now on I might try to just take a vitamin D when I'm having it, or when I feel like I'm having it. Like today I took a vitamin D, but I took it kind of thinking that it would prevent it from happening, but it still happened anyways. And I wonder if it would have been better if I just took the vitamin D when it just started. So I'll have to try it out. We'll see. I've had this thing for so many years, and I feel like I'm still like learning of like, the best ways to tackle it. Declare stack and push first all left nodes in the stack when popping out push right node. Yeah. I mean, I already solved this question. I'm just trying to make sure that I remember what the solution is. Vitamin D with calcium. Yeah, I do have a bunch of other vitamins, but most of them are actually at work, which I actually wonder if I should just bring all the vitamins back home. Chewing on something sour. Yeah, maybe I could try some massage stuff. Yeah, it's tough. I'll keep trying different things though, for sure. Anyways, while root, we're gonna self.s.append the actually we'll just call this cur to, well, actually I think we can just say root, right? Then at this point we can just move our root to root.left, which I think that's it. So basically what this logic just achieved was we moved the root all the way to the left, right? and our stack is currently at 7.3, and we want to have a next which moves the pointer to the right and then returns the number at the pointer. So this will simply pop from the current stack, right? S.pop, and we'll also just return cur.val. And then the thing is, right, again, we can't just keep our stack the same. There could actually be something. So while cur, we're going to move our cur to the right. So cur.right, cur is equal to cur.right. And if there is something there, we're going to self.s.append cur. I believe that's what we want to do. So we have I think that's it. So we're basically saying while we have something, while cur, and we say we move to the right, which we have nothing in this case. So we actually don't do anything here. We don't append anything, we're done. The next time we hit this again, the 7, we pop, and while cur, we're gonna move this now, and this is pointing at the 15, and we're going to append, wait, this is wrong though. Oh no, this is wrong. We actually want to go right, and then I know that I need to go left. The thing is, while cur, I need to go right. I can append this, and then I need to go, so while cur dot left, self dot s dot append cur is equal to cur dot left. Is this right? I don't know if this is right. This looks so jank. What's up, Desu? How you doing? Let me just verify whatever I just wrote is optimal or not. Yeah.
Rewrite them. I'm not gonna do that though.
Yeah, I see. Yeah, we just immediately put it to the right. So instead of putting it in the while loop, we just say cur is equal to cur.right. And then we say while cur, right? We'll append it, and then we'll go cur left. And then we can just remove this. This is way cleaner. Yeah, that's right. Because we only have to do it once. That's the thing. We do it once, and then we go left all the way. So that makes sense. Go 7, then we go right, while cur, s, append 15, then we go left, and we keep going left. And if we have next is all based on whether or not self.s is not equal to null. If it's not equal to null, then we have stuff left in the stack. Oh, I probably shouldn't call this cur. I'll just call this cur node, so we don't lose the reference to it. I'll call this cur node, and then cur will be set to, yeah, this should fix our issue. Alright, that's cool. This is technically a little more memory efficient, but the DFS solution probably is better time complexity wise. I think, yes, because it's always an O of 1 time. Which, to be honest, maybe I should spend some time to just try it. So basically, if I wanted to just DFS do this, right? Why don't we just call this S in order, and we'll initialize this to an empty array. And let's say we wanted to just DFS do this, right? Why don't we just create a helper function, because why not? So if not root, return. Otherwise, we're going to traverse through. So root.left. If root.left, we're going to say DFS of root.left. If not, we will just simply s.append. And actually, what am I saying? This should be self.inOrder. Self.inOrder dot append root.val, and if root.write tfs root.write. And by the end of this, we should have our in order traversal, right? And we can also initialize our pointer to 0. And basically our next, we can just say cur val is equal to self.inOrder of self.I, right? And we can just return cur val. But also, let's just make sure to increment our I pointer +1. And if we have next, this we can just check based on if self.I is less than the length of self.inOrder. I think this should work iteratively. Okay, it didn't work, and that is not good. Why didn't it work? Self.inOrder.append root.val. So what are we doing? If root.left. Actually, I don't even need these checks. This is redundant. Self.inOrder, self.I, I+1. How is it out of range? Actually a bit confused. Self in order, not root return, this root.left. Why don't I just print? I just want to see what I have in here. Oh, this didn't do anything. Should I just call it node maybe? Maybe that's why. Am I dumb? If DFS node, if not node, DFS node left. Self in order append node val. So I'm saying go all the way left. Shelf in order append node val. Self dot in order without a pen. Oh my god, I never called the DFS. I'm a fool. I am a fool. Oh no, I should never forget that. Yeah, so time complexity wise, this is faster. It's a trade-off. The iterative is not necessarily bad, but I think that's a good thing in an interview setting. It's to know the pros and cons. It's really what they want you to care about. Okay, well, I learned something there. Why don't we just go through, write some notes. Binary search tree iterator. This is a medium. Damn. I can solve this iteratively and recursively. Pros, trade-offs, depending on the solution. Iteratively is on average O of 1 time, technically slower than the DFS solution, but the space complexity will be O of H, where H is the height of the tree. Okay. That makes sense. Oh god. A hard question next. Expression add operators. Oh god. I feel like I should just maybe look at the solutions for these and not waste too much time. What kind of role am I targeting? The position that I'm interviewing for is called infrastructure. So I think with Meta, it's either you go as a software engineer, you either choose product or infrastructure. But it seems like I'm applying for the infrastructure role. So I think it's just more targeted towards back-end related stuff, which is probably going to be their focus on testing me when I have to study systems design. Am I targeting trading companies? I don't know. Not right now. I mean, I'm technically only studying right now for Meta because I have an on-site with them next month. So I'm studying for the on-site. That's why I'm only going through the Meta list. Things might change, we'll see. Given a string num that contains only digits in an integer target, return all possibilities to insert the binary operators and or star between the digits of num so that the resultant expression evaluates to the target value. Note that the operands in the return expression should not contain leading zeros. Note that a number contains multiple digits. Okay. Oh, return all possibilities. Oh my god. Is this not like a backtracking problem? Basically, this is saying you can either choose plus, minus, or star. This one's a little difficult, I feel like. I don't know about a little bit, but I feel like it's probably very difficult. What's up, Kamari? Prepare with Linux, OS, and networking. OSI model is a must. I guess I'll learn that when I get there, but I probably won't be studying that for my interview prep. I don't even know if I'll be using Linux for my work. We'll see. I haven't, up until now, I would say I haven't really needed to use Linux. Alright, so basically we're given a number, right? So 1, 2, 3, and then like a target is equal to 6. And they're basically saying they want all, so you can either choose a plus, a minus, or a star, which means multiplication, right? So you have 3 choices for every, I guess, in between. But also we can also have like a number like 101, and in this case they're actually saying you can't have a leading 0. So this means that you can either only break this into 1, 0, and a 1, or it could be a 101. It's a lot of edge cases, I feel like, that make this problem difficult. But I feel like the intuition, or what I'm thinking about, is when I see this 1, 2, 3, it's like from 1. Now you can either choose plus, minus, or star. 2, plus, minus, or star. And then 3. So I guess at any point there's n minus 1 operations, right? Because in this case we have 3 numbers, but we have 2 operations happening. But this is also depends, because we also have the choice of not only making them single digits, we could technically combine this 1, 2, 3 into like 12 and 3, right? So in this case we could just have 1 operation, right? Or we could also just have 1, 2, 3 as a number in itself, which is very interesting. I'm 20. If I learn coding now, is it too late? No, it's never too late. It's never too late to learn anything. I think the earlier you can, truly understand that that is the case, then, I feel like 20 is like the perfect age to learn. Like your brain is still, not even degrading at this point. I think your brain is still developing. I think your brain starts to like not work as good, once you're past like 25. I mean, I'm old, dude. Like I'm still learning, but I don't let age be a factor of whether or not I want to continue learning or not, Even like you'll have grandmas or grandpas getting degrees in college, It's really never too late. Infra, they will ask you easy to medium. Really? You think so? I really hope so. That would be ideal. Mac and Linux more or less have the same CLI commands. That's fair. I just know like the basics, like ls, cd, all the basic stuff. I mean, I'm sure I'd get way better at it if I needed to use it every day, but I don't use it that much. I feel like I should just look at the solutions for these, because I don't think it's worth my time to try to figure these out. So I think I spent enough time trying to like think through my thought process. I could look through a hint, I guess. Yeah, number can contain multiple digits. I already said that. Recursion. It's a recursive problem. I hate recursion. I'm always so bad at recursion.
Are you stuck trying to debug the same problem with cursor? My one child Leetcode. It's the professional software engine.
Welcome back to the Cracking Fang YouTube channel. I want to apologize for the lapse in videos. My MacBook Pro died on me, and by the time I got repaired from Apple, it's now been 2 weeks later, so hence the lack of videos. Anyway, we are now back, and today we're going to be solving 282 expression add operators. So let's read the question prompt. Given a string num that contains only digits and an integer target, return all possibilities to insert the binary operators plus, minus, and or multiply between the digits of num so that the resulting expression evaluates to the target value. And note that operands in the returned expression should not contain leading zeros. So let's look at an example and think about how we might solve the problem. So we're given the nums 1, 2, 3, and the target 6, and we're essentially told you're allowed to place anything between the digits as long as it's a plus, a minus, or a multiplication, and however you arrange those values, it doesn't matter. All that matters is that your final target is 6. So I guess let's look at one potential answer here, and we can actually see that if we multiply all the values, we're going to get 6. So if we simply put multiplication between all the values, we'll get 1 times 2, which is 2, times 3 equals 6. So this is one potential solution. And what could be another solution? Well, actually, if we add all the values, we can also get 6, right? So we get 1 plus 2 plus 3, and this equals 6. And note that even though we're using single digits here, we could actually do something like 12 plus 3, we could do something like 12 minus 3, we could do 1 minus 23. So we're not bound to just using a single digit, right? So essentially what we want to do is we just want to figure out all of the ways that we can actually get, our target value here. And unfortunately, there really is no trick to this question. What you want to do here is just, a depth first search and with some backtracking to generate all possible values. So essentially what you're going to do is you're going to start at the first value and you're going to say, okay, what are the 3 paths I can take from here on the
Okay, I knew it was backtracking. I knew the algorithm.
next value, right? And there's actually 4 paths, and we'll see why. So we can say, okay, well,
Recursion is easy AF. Dude, I don't know. Can you share me resources that I can learn from to make recursion easier? Because I feel like, I don't know why. I feel like it's so hard to like come up with a recursion that I've never seen before. Like I understand like the pattern of, yes, you always need a base case. You always need to traverse. But like sometimes like figuring out what to return at the end or even like as during the DFS, I just don't understand.
the 1 on the next value, we can do 1 plus 2, or on the next value, we can do 1 minus 2, and then on the next value, we can do 1 times 2, and then continue on, right? So we can have 1 plus 2, and then we could do 1 plus 2 plus 3, we could do 1 plus 2 minus 3, we could do 1 plus 2 multiplied by 3, and on and on and on, until we exhaust all of our values, and then at the end, we can actually evaluate all of these expressions. So this is 6 here, this is going to be 0, so obviously that doesn't work. This one is going to be 7, because we want to deal with order of operations. So what we do is just we build all the possible values, and at the end, we're going to check whether or not they equal our value here, and if it does, then we can add it to our result, and we're good to go. So the way that we want to do this is we want to, like I said, do a depth first search, and we're going to be using some backtracking here to basically explore all the possible options. And what we need to do is we need to keep track of, our current index, because that's going to tell us where we currently are, right? So we need to keep track of our index, pretty straightforward. What else do we need to keep track of? Well, we need to keep track of the, solution that we built so far, right? So here, if we were at the point where we're doing 3, our
Oh, your professor was awesome. Yeah, I never took data structures and algos in college, so I'm basically self-taught.
solution state so far would kind of look like the string 1 plus 2,
Unlucky.
right? So we need to keep track of where we are at each stage. So we're going to say the current results is what we want to keep track of, right? We want to keep track of our current results, and we also want to keep track of the current sum, because obviously we don't want to be evaluating the sum every single time. We kind of just want to be doing it on the fly as we go. So we're going to say the current sum. And that way, when we get to the end, we don't then have to sum over everything. We can simply just check whether or not the current sum equals the target. So, and then the current number is the last thing we want to keep track of. Obviously, we just want to keep track of that. And the reason that we actually want to keep track of the current number is because you have multiplication. And with multiplication, unfortunately, we're bound by the order of operations, right? So if we were going left to right, obviously we would process the 1 and the 2 first. So technically, we would have added 3. And if we get multiplied by 3, we'll get 9. But we know that our solution is 7 because we need to actually multiply the 2 and the 3 first, and then add the 1, which gives us the 7. So the reason we need to actually keep track of the current number, which when we get into the next iteration will be the previous number, is that we would need to undo any sort of
This question has so many things to keep track of. No, this like, if I get this, they want you to fail. This is ridiculous. Let's see what the comments say. Toughest question I've seen, even after reading the whole thing, I can't get it. This question is too hard. I can't believe I do not believe anyone can solve it during the interviews. I agree. This question is a great example of how ridiculous the interview process has become. Okay, Zuck, why don't you just ask me to cure cancer instead? These guys are too funny. Wait, this guy's name is Bleh. Is this you, Bleh? I was asked this question in Pinterest, and thankfully this was on Leetcode, and I was able to solve it and move to on-site. Jesus Christ, this is too sweaty. I only know like 3 or 4 that found it easy. No way. I feel like most people, like, for sure. I think like 99% of people that see this question for the first time, there would be no way they solve this. No way. I refuse to believe it.
Addition that we did before, and then we would multiply our current number times the previous number to get that result, and then we'll add back the value that we had added previously. And this is only in the case of multiplication. If it was just addition
What's the strat? I don't know. I'm trying to figure it out.
and subtraction, this problem would be a lot easier, but unfortunately we have to essentially keep track of the multiplication case here.
Oh, I was talking about recursion. Oh, I see. I thought you were talking about this problem. I mean, I get like, the basic stuff, like generally like how in order, post order, pre-order, stuff like that goes. But when it comes to like applying it to Leetcode questions, I feel like it's not easy to come up with the solutions. And not only that, I guess to code it well without any mistakes. I don't know. Because like for things like arrays, I feel like I can verify what I'm doing very well. Or not very well, but more so I can follow what I'm doing. When it comes like with BFS or DFS, I feel like DFS, I just can't truly know if what I'm doing is right or wrong.
So we are going to need to undo
I just did a min stack question. Nice.
any sort of addition or subtraction that we may have done in the case that we have that. And one last thing that we want to be careful of is this thing here, right? We don't want to have anything that contains leading zeros. And what might that look like? Say our numbers are 105, right?
Yep, I said
and we
this.
know that we could split this like 1 plus 0 plus 5. That's fine. We could split it like 10 plus
Oh, you could have 1 plus 0 plus 5. Oh, I didn't even consider that.
5. But what we can't actually do, and if we kind of make some more space here,
You
we can't
can't-
say 1 plus 05.
Yeah, you can't do
This is not a
105.
valid number. We cannot do this because obviously the numbers should not contain leading zeros. So we're going to need to add a check in our code to actually make sure that if we have a 0, then we want to force, you know, going on to the next value. We don't want to accidentally keep parsing it as if it was one number, right? So if we had like 1, 2, 3, we could parse the 1, but then we could also build a 2 out of it and then make it 12 and then add the 3, right? We can't do this when we have a 0 because, again, we cannot have leading zeros, so we can't do the same thing that we did with the 12 here. And, you know, similarly, if we did 1 plus 2, we could then make that 2 into a 23 if we wanted, but again, we can't do that with the zeros here. So that is how we want to solve it conceptually. But what we're going to do now is we're actually going to go to the code editor because I think it's going to be a lot simpler. This question, obviously, it's a depth first search.
Yeah, I think I need to do more backtracking. I do feel like backtracking is like more of a, yeah, it's just like another DFS. I don't know if it's correct to say variant, but like, you know, it's I'd say a more advanced use case of DFS compared to like just traversing through a tree. So yeah, I guess in that sense, maybe I think I just need to do more backtracking questions or just recurring questions in general.
With backtracking, so there's a lot of possible options that we could take here. For each path, we have basically 4 routes that we could take, and essentially we want to you know, enumerating this for all the possible values, it's going to get real messy real fast, and it's easier for me to actually just go into the code editor, type this up for you guys. Anyway, I'm going to stop rambling, so I'll see you in the code editor momentarily. Let's type this up. Back in the code editor, let's type this up, and it looks like Leetcode actually has a new UI here. It looks pretty clean. I kind of like it. What do you guys think? Let me know in the comment section below. Anyway, let's get into the problem. And the first thing we see is that we need to return a list of all of our results here. So let's define that variable, and we're just going to say res is going to be an empty list. Now we actually want to define our DFS function. And I guess before we do that, we can just return res at the end, right? Cool. So our DFS function basically needs to do all of the work. So we're going to say def DFS, and remember the things that we're going to take in is going to be our current index. We're going to take in our current result. We're going to take our current sum, and we also want to know what the previous value was, right?
Like, if you've never solved a problem like this before, like, how are you supposed to know that you needed to initialize all 4 of these variables? I feel like there's just no way you know. Like, yes, if you've seen the answer before, of course you'd know now, but like, how the hell are you supposed to know this?
And remember, the previous value is the cases where we actually need to do multiplication, and we need to undo any previous addition or subtraction that may have happened because order of operations. Okay, so the first thing we want to do is actually check that we haven't overran our number here, so we just want to add a check that our index is still valid because we don't want to get any sort of index errors. So we're going to say if the current index is actually greater than or equal to the length of num, then what we want to do is we want to check if the current sum equals to our target, then we know that we found a solution. So we want to say res.append, and what we're going to do here is we're going to basically you know, join together our current result, and we're going to join the current result. And
Wait, so if the current index is greater than or equal to the length of nums, this means we're done, right? So if so we're checking, I guess. Okay.
and we will add that to our result. Cool. That's what happens when we have a solution, and you know, at this point we need to return because obviously we're still in this if statement, so we don't want to continue going further. So now we need to do the else clause, and what we need to do here is we need to build out all the possible values, right? So say we had like 1, 2, 3, we need to build out 1, we need to also do 1 and 2, and we also need to build out 1, 2, 3. So we need to basically
Oh, wait. Oh, wait. So you need to use all the numbers. Oh, so you need to use all the numbers. Oh, yes, of course you have to. Otherwise, then this would probably be a possible solution. You could just do some way to get 9191. Okay, so you have to use all the numbers. All right, that makes the question a little bit easier, I guess.
we go through all of those possible values and then explore all of the subproblems inside of it. Like I said, this is going to be a depth first search problem with some backtracking, so we need to keep track of basically all the possible options that we can go down. So we're going to say for I in range from our current index to the length of num, we're going to say that the current value is going to be the num. So we're going to parse the current index. So
For I in range, the current index.
we're going to say cur ix from our current index plus 1. And the reason that we want to do this is remember that we can possibly parse out. So if we had 1, 2, 3, we don't want to just parse out the 1. We can parse out the 1 and the 2. We can parse out the 3. You know, if we had a lot more numbers, we would just keep going. So we don't want to just stop it.
That's correct. You need to parse through all of them.
Single digit, we want to be able to parse as far as we can possibly go. So that's the reason why we go from the current index to basically index plus 1. So that's going to basically parse them all out. So we're going to
Jesus Christ.
get a current string here. Obviously, this is a string here, so we need to basically convert it to an integer because we're going to be working with some sums here, so we want to make sure it's actually an integer. So we're going to say the current num is just going to be integer of, our current string, right? Cool. So we've now parsed, a current number, and now what we need to do is actually just explore all of the paths, right? So one thing that we need to realize is that if we're at the very first number, so if we had 1, 2, 3, obviously our current result is going to be empty because we haven't parsed anything. In this case, we don't want to be adding anything. We just want to parse the first value and then move on, because obviously we haven't done anything yet. So we need to just parse that first value so we can continue with our function. So we want to check. Let's see, am I inside my loop? So no, we're going to say if not res. So if we haven't parsed anything yet, this is our very first index. So basically the index 0 in number. What we want to do is we want to say dfs. So obviously we're going to increase the index plus 1, and then our current result is just going to be that first value. So it's just going to be the current string. And then what we're going to do is, our sum is just going to be the value kernum, and then the previous value is just going to be kernum, right? Okay, so we pass that in, and why is it giving me? Okay, that's weird. I should know. Anyway, that's what happens for the first value. Otherwise, if we have any other value, we just want to proceed normally. So let's do the addition case. So obviously our index is still going to get incremented by 1. Now what we want to do is we want to take our old current result, and since we're going to be doing an addition here, we actually want to do a plus here. So we're going to add a plus, and what we're going to do is we're going to add the current string. And so basically we take our previous result, we add the plus, because remember our result needs to be actually a list of strings. So we need to build out this result. So this is basically kind of us doing like a string builder here. So we're going to say current res plus, basically we're going to add a plus operator, and then we're going to add the plus
Wait
value.
a minute.
So one thing that we need to realize is that if we're at the very first number, so if we have 1, 2, 3, obviously our current result is going to be empty because we haven't parsed anything. In this case, we don't want to be adding anything. We just want to parse the first value and then move on, because obviously we haven't done anything yet. So we need to just parse that first value so we can continue with our function. So we want to check. Let's see, am I inside my loop? So no, we're going to say if not res. So if we haven't parsed anything yet, this is our very first index. So basically the index 0 in number. What we want to do is we want to say dfs. So obviously we're going to increase the index plus 1, and then
If not res.
our current result is just going to be that first value. So it's just going to be, the current string. And then what we're going to do is, our sum is just going to be the value kernum, and then the previous value is just going to be kernum, right? Okay, so we pass that in, and why is it giving me? Okay, that's weird. I should know. Anyway, that's what happens for the first value. Otherwise, if we have any other value, we just want to proceed normally. So let's do the addition case. So obviously our index is still going to get incremented by 1. Now what we want to do is we want to take our old current result, and since we're going to be doing an addition here, we actually want to do a plus here. So we're going to add a plus, and what we're going to do is we're going to add the current string. And so basically we take our previous result, we add the plus, because remember our result needs to be actually a list of strings, so we need to build out this result. So this is basically kind of us doing like a string builder here. So we're going to say current res plus, basically we're going to add a plus operator, and then we're going to add
So I need one for everything, right? Plus, star, and minus.
the current string, basically keep building it out. So right, if we had like 1 in our current result, we're going to add a plus, and then we're going to add a 2 if the number was like, 1, 2, 3, right? So that's what we're doing there. So that is the part where we actually build out our current result. Now our current sum, essentially we're just going to take whatever the current, previous value was for the sum, plus adding our current num to it. Pretty straightforward. We're just adding our current value to the old value. And what we're going to do now is we need to just update our previous value for when we go into the loop again, and the previous value is just going to be our current
Curse sum?
number. Okay, simple enough. Now what we need to do is we need to go into our dfs function. Why is this yelling at me again? Prev. No, it's right here. Okay, it's weird. Let's see if it just goes away on its own. I don't know what Leetcode is doing.
Well, he doesn't have anything called curse sum.
I'll turn this off. This is the new UI. Anyway, again, we want to increment our value here. So we're going to increment our value, our index, sorry. And again, we're going to do curres, and we're going to do curres. And this time, we're going to add to the list a minus operator, and we want to add a
I'm surprised he's not copy and pasting everything, but sure. Oh, I see. So he'll add it, then subtract.
string. Again, it's the exact same thing as the plus case, except for we want to just add the minus here. And again, this time, since we're subtracting, we want to say the current sum minus the
Oh, we're just... Okay, so the res is basically to keep track of what the actual string looks like. Which makes sense, because we're saying go with 1, then we add the star, then 2, then 3.
current number. Obviously, we're doing subtraction here, and now the current num will just be minus current num in this case.
Minus kernel. Yes, that makes sense.
And that's all we need to do. So let us now move to the multiplication case, which is the most complex case, but luckily we have set ourselves up for success here. So again, it's going to be the same kind of pattern. We're going to, instead of a minus, we're going to add a multiply here. And again, we're going to add a current string. Pretty straightforward. Now what we want to do is we need to undo the results of any previous addition or subtraction that we may have had. So
Oh my god, it's this question like this again. That's right, because to solve questions like these, you need to undo anything you've done. And then, yeah, that's
we need to do
annoying.
that. And the way we're going to do that is we're going to say the current sum minus the previous value, oops, minus prev, plus the current number, plus the previous value. And let's kind of sanity check this so you guys can see this works. So say our number is 1, 2, 3, and say we had 1, 2, and now we're going to multiply by 3, right? So our result up to this case should be 3, and we want to multiply by 3 now, right? And this would give us 9, which we know is not correct because order of operations says that it should be 7. So let's think about what our current sum is, right? Our current sum would be 3, and the previous value would be 2. So what we're going to do here, let's look at, okay, what's the current sum? So 3 minus 2, and what we're going to do, right, obviously that equals 1, and to 1, what are we going to add? We're going to add whatever the current number is, so it should be multiplied. We're going to add to it whatever the current number is multiplied by the previous. So we know that the current number is 3, oops, so we're going to say, 3 times 2, which we know is 6, plus 1, this will give us 7. So there's how you get that value, and this is how it works. So basically, this part is undoing the last operation. This part is applying the current number multiplied by whatever the previous number was, and that's why we have previous in our function here. We need it for this case here. If we were just doing the addition and subtraction, we wouldn't need it, but unfortunately, because of the multiplication, we need to keep track of previous. So this is where it comes into play to basically undo the order of operations and make sure we get it the right way around. So that is the...
I see. So basically, you're subtracting the previous thing you just added, or subtracted, I guess, depending on the operation, and then you're adding it to the thing you're multiplying, because that takes precedence over.
Actually, we still have to basically define the previous value. So now in this case, it's going to be kernum times previous, right? So that's what we want to do. Now, what we want to do here is there's one last check that we need to do, and that is, again, for that trailing zero. So right, for like 105, we can't have 1 plus 05. It either has to be 1, let's see, 1 plus 0 plus 5, or 10 plus 5. We can't have this 05 here, so we just need to check if we've actually started on a, you know, a leading 0, then we have to make sure that it's on its own. We can't continue through this loop here if the first value here, I, actually gives us a 0. So we're gonna add a simple check for that. We're gonna say if the current num of whatever the current index is actually equals to 0, and remember that num is actually a string, so we actually need to check for string equality here. We just want to break out of this for loop. We don't want to continue making it, right? Because again, if we look at 105, what this loop is going to do, it's going to get 1, or it's going to take 10, or it can do 105. And if ever we started on a 0, we don't want to parse, you know.
If the current index 0 break. That's right. If it's a 0, we only add it for the 0, right? That makes sense, I guess. And because anything after that point, you're adding more numbers, which you don't want to.
No, we don't want to do.
Clever.
We want to do 0 and 5. We don't want to do 05 because that wouldn't be correct. Because again, the problem says no leading zeros. So that is your DFS function. The last thing we need to do is actually call the DFS function. So let's call DFS. So the current index, obviously we start at the 0th index. Obviously our current result is empty when we start, so we're just going to pass an empty list. Our current sum, we haven't done anything yet, so it should be 0, and the previous value should be 0 because we haven't seen any values yet. So let us run this. Hopefully I haven't made any mistakes because this problem is quite complex. Okay, it seems to be accepted. Let us submit this and judging what happened. Okay, cool. So we are done here. That looks like it was accepted. This is a new UI, but okay, it seems fine. Yeah, solution was accepted and kind of got lost.
Okay, wow. You know what? I mean, just looking at the code, it doesn't look that bad, but dude, coming up with the solution is crazy. It's crazy talk. Okay, so basically, I feel like the hardest part is figuring out what you need during this DFS. So basically, you need to keep track of just backtracking, right? Backtrack with a res, sum, and prev. Is that it? As well as the index, of course. So as you go through this, basically what we're saying, or how this is gonna look. So let's just go through. Let's just first go through this case, with the 1, 2, 3 simple case. So we're basically saying, right, we're gonna start with this 1, and we're gonna say 1 is our current num, I guess. And there's, I guess, a base case, which I guess our base case is if our current index is greater than or equal to the length of num. This channel, he made a video on how to code and passing Nang. Who is Nang? This guy?
Alright, so today we
Oh, I know this guy though. What's his name? Frying whatever? Frying pan or something? Oh, I watched this video. Making an AI OnlyFans with computer science. That's good clickbait. I haven't watched anything else. Wait, what the hell? Why is he talking to Fan? That's so random. Which video is it though? Popular? Cracking, is it this one? Cracking software? No, I don't think so. Full guide? Full guide. Oh, this one.
Today we're going to be going over a full guide to coding interviews. And my promise to you is that if you follow everything in this video and get an interview at FANG, you'll get the job. Yes, a very big promise. This video is going to be a little bit different than my normal videos. It's going to be strictly business in this presentation form because this time I'm actually trying to provide value for the first time ever in my life. So this is the schedule for today. First, who I am, so you'll listen to my advice. What theory you need to know, the formula I use to help with most Leetcode problems, how to practice and improve for these coding interviews efficiently. Then I'm going to go get lunch. I'm probably feeling some sweet green. If you haven't had it, you should try it. Then we're going to be going through a live example of exactly what to do during these coding interviews. After that, we're going to be going over the behavioral part of the interview and how to prep for that. And finally, some advice. Pretty much, I'm trying to make this video what I would have wanted to see when I was starting out with these coding interviews. But yeah, hopefully it'll be helpful. Maybe it will, maybe it won't, but we're doing it anyways. So first, who I am. Pretty much all that matters on YouTube is FANG. So yes, I got jobs at FANG. I also just graduated from CMU and
Where am I from? I'm from the US, I guess.
some YouTube videos that you guys should check out. Now I work in high frequency trading, and if you don't know what that is, don't worry about it. Just know that you can trust me. Maybe.
Oh, he's in high frequency trading, so he makes a lot of money now.
Man, I don't even know. All right, so now let's talk about the theory, and this is the part that you absolutely need to know. These are some data structures and algorithms, and I guess I'll read them out for you.
Thankfully, I don't need to know DP. I feel like I've seen all these data structures now, like a decent amount. I still think I need to work more on backtracking and graphs, but heaps I feel like I've been getting a lot of practice in, as well as linked lists. Trees I feel like I could still do better in.
We got arrays, stacks, queues, maps, trees, linked lists, graphs, backtracking.
You can check his video in your spare time, fair enough, but to be honest, I don't know if I'll be watching his like more meme type of videos.
Dynamic programming, and heaps. So how you can learn these are through a university or online course that's usually called Data Structures and Algorithms, and then on top of that, through YouTube videos. Hackering is probably the best for the base understanding of these, and they have a video for all of them with the animations and stuff. It's actually really good. And there's also this absolute goat named Abdul who explains a lot of this too. You're gonna need to understand how they work, all the time complexities, how to code them up, and if you don't know how to apply them on this part just yet, don't worry because that'll come up later. And I'll be putting up a cheat sheet that I use to review before every single interview about all these data structures in the description. Okay, so now after you spend some time learning those, here's a formula that I use that helps with a lot of these Leetcode problems, and I guess I'll read it out again.
If an input array is sorted, yes, binary search is pretty obvious. 2-pointer, okay. If given a tree, BFS, DFS, yes. If asked for all per combinations, yes. This is why I thought of backtracking for the current problem I'm doing right now, because it's asking for all the basically combinations. If given a graph, then BFS, yes. DFS. If given a linked list, then 2-pointer, probably, yeah. If recursion is banned, then stack. Yep, that makes sense. If asked for a minimum, maximum subarray subset of options, I don't have to do that, thankfully. If asked for top K, yes, heap. If asked for common strings, then map or try. I have not really ever worked with tries that much. I'm starting DSA, it's so scary. It's okay, just take it one step at a time. I'm not that great at it, I feel like, still, but you know, I'm definitely better than I was yesterday, so I guess that's all that matters. If you want to keep count of distinct elements, map or set. If asked for common, yeah, and then sure.
Yeah. If the array is sorted, then use binary search or 2-pointers. If a tree is given, then use DFS or BFS. If you're asked for all the permutations or subsets of anything, then use backtracking. If you're given a graph, then use DFS or BFS. If you're given a linked list, then use 2-pointers. If recursion is banned, then you want to use a stack. If you're asked for the maximum or minimum of some subarray, then you're going to be using dynamic programming. If you're asked for the top or least k number of items, then use a heap. If you're asked for the common strings, then use a map or a tree try. If you need to keep count of distinct elements, use a map or a set. And else, you're probably pretty set if you just go with a map or set in your problem. And you can also try sorting the array and going back to the first if statement. And yeah, I think this formula can help with the first step for a lot of these problems. Okay, so now how do you practice efficiently? I've watched a ton of videos about this, but I think this is what helped me the most. You go to the Leetcode FANG list or grind 75 and do one problem from this a day. You try the problem, and if you don't know how to solve it,
one problem a day, that's it?
which is going to be super common starting out, then look at the solution. Figure out how to solve it based on the solution, and then give it an hour or so, and then type the solution out yourself by the end of the day. This is not so you can memorize the solution to the specific problem because that doesn't matter. Instead, you want to get a sense of how to think about the problem, and you can do that by seeing how other people solved it. The most important part is consistency, like doing at least one problem each day. And then honestly, it takes time, like for each person, it's different, but eventually you get to a point where you don't have to look at solutions anymore, and you can just figure out the problems on your own. Also keep track of which problems you solve in a spreadsheet.
That's crazy. I mean, I'm still not there yet. I don't know how many problems it's going to take for me to not have to look at solutions, but I feel like I don't know.
And I'll leave a template for this in the description. Okay guys, so now we're going to be looking at a live example of exactly what to do. Here is a question that's really common, and I'm just going to leave it up here for like 5 seconds. You guys can pause and read it on your own time. And there's a couple key points that you should know for any interview that we're going to be.
You're embarrassed? I mean, I feel like the way he is like, he's very memey, which there's nothing wrong with that. I mean, I think it caters towards a certain audience, which is, it's good. It's good. But it's definitely like, I think he's more targeting towards like, you know, gamers or people that are, how do you say, they're just not normie. Which I'm like that too, you know. Like I like things in meme format, but it really depends, I guess, on your target audience.
Going over. After you first read the question, I would reiterate what you think the problem is asking you to your interviewer, because that'll just clear up a lot of confusion if you like are completely misunderstanding the problem. Here I would tell my interviewer something like, okay, so this problem is giving us a matrix of ones and zeros, and we have to return the number of islands, which is defined by a group of ones surrounded by all zeros or edges of the matrix. And then they'll say like yeah, or they'll correct you if you're wrong. But in this case, I think that's what the question is asking. And I'll say you don't need to ask clarifying questions if you don't have any. But I guess one question you could ask here is, does diagonal land count as being adjacent? Which is a pretty obvious question, like it's either horizontal or vertically, but maybe you're misreading something, and yeah, the interviewer would be like, yeah, no, diagonals do not matter. For pretty much all these problems, I would start out by thinking about how you would do the problem as a human without any computers. So if I was trying to solve this problem, or like a 5-year-old kid was trying to solve this problem, to count the number of islands, we have to find a one somewhere, right? If it's all zero, until we see another one, and then
I mean, this is obvious.
that one is
like obvious.
So first we see this one here, and that solution, so we're gonna return it. Then we're gonna
He's just solving. I don't really care about this though.
add to our visited set. Not gonna be 100% sure, but we can try.
I don't know. I mean, I already know like a decent amount of this stuff. Like I get it. I don't think I need to watch the rest. I don't think I need to see him code up a number of islands. But that cheat sheet is nice, I guess. But again, I feel like I know everything I need to do. It's just putting in more time, you know. It is what it is, I guess. It is what it is. So I guess our base case, right, for this is like if at any point our IDX is greater than or equal to the length of nums, this means there's no more nums to process, which means we're just going to see if it's equal to the target, we can add it to res. Otherwise, we don't do anything. How many questions have I solved? That's a good question. I think, let me double check. I don't know if I hit 200 yet. I think I did. 257. But to be fair, I think the problem is that I don't do it all the time. Like if you look at my, you know, activity, the thing is like I have phases. I mean, look at this, like, bro, I legit just stopped. Like, I don't know. I always have like breaks in between, which I think is really bad. And before this, it took like a 2-year gap. Like, I still feel like I'm getting better, but I definitely could have been way better faster if I just decided to like make it a lifestyle, which I think if you're in this space, it kind of just has to be if you want to improve. I'm just like that. I think that's just like the way I am. I mean, even like Valorant or something, you know, like I'm a high rank, but I'll still say things like I suck. But I think that's the like, I think I'm just always like, I don't think I'm ever satisfied, you know. Like I always think I can be better. I can do better. Like unless I was like top rank, if I was like legit like rank 1 or top like 1%, I think maybe I'd feel like not as, you know, newbie. But I still feel like objectively speaking, I'm probably like maybe like gold or plat, maybe rank, I'm not sure. I just try to be objective about it, but also I am like, the way I speak is kind of harsh, but yeah, that's just how I am, I guess. I think I'll feel maybe more confident if I solve like 400 questions, but at the same time, I think I just need to do it more. I don't just do it every day, so I definitely just need to do it every day. Like just one problem a day doesn't hurt. Asian thing, maybe, I guess so. I mean, my Asian, like my parents were always so, they wanted wanted A's all the time. Or B's, I guess. I remember I got my first C plus in Calc BC. And my mom flipped out. I'm just like, bro, this is cancer. Get me out of here. Alright, so okay, this makes Asian parents, yeah. It is what it is, you know? But I'm not with my parents anymore, so I'm a free man now. Life is better this way. Having independence is a nice thing. So I guess let's just kind of go through this whole problem, right? So we're going to have a create a function called defDFS. And like we said, we're going to have an I pointer that's going to point to the nums of I. We're going to have a path, which basically is going to denote, you know, which path we're taking. We're going to have curSum, which is going to let us know our current sum, and previous to keep track of the previous value. I guess this is used for the case that if we ever needed a previous and we have to deal with multiplication, we can undo it and go do that. My mom cried because I got a B plus. Yeah, dude. Yeah, my mom cried too. And then she was like, saying like, what did I do to like raise a child like so wrong? I'm just like, bro, it is not that serious. Like you are crashing out, and I don't understand. It's just weird. It's just weird. I feel you. But it's okay. It's okay. I'm out of that now. That was in my past. So that was like probably like over a decade ago at this point. I'm well past that phase of my life. Geez, that's harsh. It's okay. It is what it is. I'm not too bothered by it anymore. It is what it is. So we're gonna have our base case. Virtual hugs, appreciate it. If I is greater than or equal to the length of num, then we can check if curSum is equal to the target. We can rest on append the path, right? We have our else case, I believe, which means we still have to process things. In this case, we want to say, I think we want to process all the possible, right? Because not only can we do 1, we can do 1, 2, or 1, 2, 3, right? So we have to do for I in range from I to the length of num, right? Once my dad contacted my middle school teacher because I had a B in math, she pulled me out of class to discuss about my situation. Bro, that is crazy. Dude, I don't understand. I mean, I actually don't know if it's like, is it actually beneficial? Is it, I don't know. Like, is it actually beneficial to be that anal about everything? I'm not sure. I feel like there's got to be better ways to raise your kid. I don't know. At the same time, some kids just aren't good at school or want to do other things in life, I guess. But I guess if they're gaming all day or just not studying, I think that's a little different. Hard to say. So we can say the kernum is from num of I to the end, right? So we start at 0. And I guess just so that we don't forget to call our DFS, we'll start at 0, empty array. Actually, I think we just make an empty string. And then cursum is going to be 0 and prev is also going to be 0. So that's how we're going to initialize it. So we start from 0 to the end, which will give us the current complete number. Actually, it's I to... Wait, should it be I plus 1, not I? Oh, it is. That's right. It's non-inclusive. I guess it all goes to how we take it, I guess. Yeah, I guess. I don't know. Everyone's different. I will say I feel like for me though, I don't think it was constructive though. Like if anything, it just made me not it just made me dislike my parents even more. But I don't know. But to be fair, I guess they didn't know any better either. So I wonder if we could have just said I plus 1. Actually, no. So we're saying for I in range, and we're going to the length of num. And also, we're going from cur idx. What is... Oh. Oh, I see, I see. Oh no, I am doing that. Oh my god, wait. Oh shoot. I shouldn't call this I. Now this thing makes it confusing. I should probably call this J. Sure, I'll call it J. And then for J, from I to J plus 1. Right? Because J plus 1 represents the same position of I. Because if we said nums of I to J, I think this would output nothing. So in this case, J would say this would be for J in range. I believe this is 1, right? From 0 to the length of nums. Then cur num is num of I to J plus 1. So 1, 2. So this is where, I guess just to visualize it. Let's just erase all this, I guess. There's a bunch. So let's just go through the example of, we have 1, 2, 3, and we have our I pointer and our J pointer. Because Python is non-inclusive, when you say the num of, give me the num of 0, comma 1, or to the end, this would just mean, just give me, this would just return 1, right? So cur num is set to 1. My dad is chill and my mom is an Asian tiger mom. Yeah, I feel like my dad is also chill for the most part. I mean, he can be savage sometimes too. But, yeah, I don't know. Alright, let's see. So we're going through this, right? So our current number is this. Now we do need to build our DFS function calls. So we gotta move our index 1 after, and also we have to add path plus star, or let's do plus first. Plus, and then curse sum would be equal to, well, what is curse sum? Curse sum is 0, and then we would just add, we would add cur num, right? So 1 and wait a minute, but it's a little confusing. Can we have -2 to start off? Maybe. I guess that's possible. An edge case that wasn't mentioned, or maybe was mentioned, but I didn't catch it. And then prev would just be equal to cur num, right? Cur num is prev. And minus would be the same thing. And actually this would be negative cur num. Then DFS of I plus 1 path plus times. In this case, we have to do the cur sum minus prev plus the previous times cur num, I believe. Then prev is going to be cur num, I believe. I think that's right. And so for current number, is there anything else we need to do here? I think this is fine. And then we have to consider our edge case, right? If at any point, if j is equal to 0, we can just break. Is that it? If not, cur res. That's right. Okay, yes, I was gonna say, yes, if we don't have anything yet, so if not, what do we say? What's cur res in this case? I think it's path. So if we don't have anything path, then we want to handle this differently. This is our else case. When we want to initialize it, we just initialize it to I plus 1 and path plus cur num, cur sum plus cur num, right? I think that's it. Int and string. Oh, I gotta convert this into an int. Can only concatenate. Wait a minute, how did he do it? Oh, he has cur string and cur num. Oh my god. That's annoying. That's annoying. And cur string. We have our cur string, which is going to be, so actually in the path we're just going to add cur string, cur sum, cur num, and this is also cur string. Do we need to add more? I feel like this is wrong. Good night, bleh. Take care. Take care. Yep. was right about this. Okay, so it's actually curse, yes, plus curse string. A lot of edge cases. Well, I guess we have hit a... Oh my god, I don't return here. Is that why? Okay, that's not why. Wait a minute. Oh, he makes it into an array? Why though? I feel like this is unnecessary. I is greater than or equal to length of num. Curse sum is equal to target. Return. Else for I in range or for j in range. From I to length of num. Not path. Oh wait, it's just kernum. Okay, this is whatever. Kernum path. Why don't we just say curse string? Sure. This else case. Oh, it's kernum times prev. It's still broken. Kernum of ID. Oh. Yeah, it's not if j is equal to 0, it's num of j. Come on now. That's still broken though. Why is it still broken? Is it num of I? Oh my god. What am I doing now? Cur IDX. How is this still wrong? Kernum. Cursum minus prev plus prev times kernum times prev. Why the heck is this wrong? Oh, it's J. Bro, what am I doing? Yeah, this is dangerous, these pointers. These are dangerous, bro. Yeah. No, it's not J. It's the letter J. I feel like the problem is not that difficult, I guess, in hindsight, but coming up with this is pretty insane. I don't know. Like, even just getting this question is insane to think about. The fact that you gotta figure out, like, the first case. I mean, there's also the edge case of figuring out. In the first case, we just have to add this to our DFS. We'll have our ID path. We have cursum and prev, which will just update all of these things to be, in this case, it's I plus 1, path is just set to 1. Cur sum is set to a cur sum is set to just 1. And prev is also set to 1. This one's a little difficult, so I would say I'm gonna reset it, try it again. So, alright, let's do this problem again. Given a string num that only contains digits and an integer target, return all possibilities. All possibilities. When it says possibilities, I think of defaulted backtracking to insert the binary operators. Should not contain leading zeros. Sure. Yeah, we gotta handle that edge case. A number can contain multiple digits. I think that's obvious. Alright, let's code this up again. So basically, we're gonna create a result variable that we're gonna store all of our results in. And our result is gonna look like this, def-dfs. And we're gonna call this idx for better naming convention, or cur index, cur I. What's a better word? I feel like I is fine. And then we can just say the path is what we need, and cur sum and prev. Because we also need to, the thing is, like, we have to handle multiplication. And multiplication, we always gotta handle that way. Very specific. Let's just make sure that we call this in the beginning so that I don't forget this call. This is how we're going to initialize our DFS, right? So there's our base case is really the fact that if our I is greater than or equal to the length of num, then there's no more numbers to process, right? And we check if cur sum is equal to the target, then that means we can append this to our result, right? Which is denoted by path. And do we need to return? I don't know if we need the return actually. I don't think it's necessary. But if we're here, then that means we still have more to process, more numbers to process. And in this case, there's actually, we're either in the middle of the loop or at the start of it. So if we're at the start of it, so if not path, right? We don't have anything. We just need to initialize our DFS to DFS of I plus 1. And actually, we're going to need to process what our current number is, right? So for I, or I can't say I, for j in range from I to the length of num, right? Because we can process 1, we can process 12, we can process 123. So cur string is going to be equal to, because we're given a string, right? And this is just denoted by nums of I to j plus 1, because the second parameter is not inclusive. And then cur num is equal to the int of cur string. that's pretty simple. And then at this point we can say in our first case, I actually need to indent all this. So we need to go through everything in the for loop, right? So for every combination, every possibility, if it's not path, so in our first case, if it's not the path, if okay, so our path would now be set to curString, curNum, and curNum. That would be our and I gotta really be careful. It's gotta be J, not I, because we're now looking at J plus 1, right? Because we're going through everything in J, because I is our current index. But is it not I? No, it's not I. Yo, what's up, Narayan? What's up, Kumar? $23, 20 with peak? What are you talking about? So I guess it's just J plus 1. Can I help you? I don't know, can I? You tell me. Why not though? I'm busy, so unfortunately you're probably asking the wrong person. So if it's not the path, we're going through J. Yeah, because J is our new pointer, right? Because J is noting basically every single possible new every possible number combination. It's basically what J is doing. Okay, so else we're gonna have to consider J plus 1, and we're doing this for everything, so it could be 12, it could be 123, and that's it. Yep. And we can have path plus could be a plus sign plus the curNum. Then the curSum would be set to curNum or curSum plus curNum, and prev would be set to curNum, right? So that's not too bad. And then let's just make sure we handle our minus case. And in this case, curSum, we do curSum minus curNum, and it's negative curNum, as well as handling the multiplication case. In this case, we actually have to undo. So we'll have to say curSum minus prev, plus prev times current num. And then this new number is actually our new prev, right? And at any point, if do we do this inside or outside the for loop? We'll do our first case, right? So if at any point, right, if num of I is equal to 0, then just break out of this. And I think that is freak. Today's curse string. Dude, that's so annoying. Okay, boom. Alright, cool. This problem makes sense, I'd say, after looking at the solution. I feel like I haven't seen too many backtracking problems. This is a backtracking problem. Expression. Add operators. I'm assuming this is the red I want. I don't know. Backtracking with making sure that we handle multiplication and what else? Also have to handle and just edge cases like at no leading zeros. But okay, sure, that's not terribly bad. Okay, so we just did this problem, right? So let's do the next question. Okay, next question is, given an n by n matrix, so it's a square, okay, where each of the rows and columns are sorted in ascending order. Return the kth smallest element in the matrix. You must find a solution with a memory complexity better than O of n squared. Okay, so the 8th smallest number is 13. Okay. You must find a solution with a memory complexity better than O of n squared. Okay, it's sorted in non-decreasing order. Always with problems like these. Let's see how we would think through this problem. So the first thing that comes to my mind, I guess, with anything with regards to something that's sorted, my mind always gravitates towards a binary search type of solution. Actually, one thing we could do is traverse through. So it's actually asking for a memory complexity better than O of n squared, right? I know that with a heap, we can achieve this with O of k, right? Because as we traverse through the matrix, and maintain a, in this case, we're looking for the kth smallest element. which means that we can maintain a min heap, I believe. We maintain a min heap. And that way we'll maintain just typing. What the hell are you saying, you lol? I'm not just typing. Maintain a, let's see, want to maintain a min heap and pop whenever we see something larger than exceed k. Watch this, chat. Watch this. So we'll just call this min heap. We'll initialize this. So for I in range from length of matrix, then for j in range of length of matrix of 0, if length of the min heap is less than k, then we can heap q dot heap push matrix of I j, right? Else once it's greater than or equal to hold up, it can be equal, right? Because we can have, if we have, let's say we have k elements, or k is our thing, and we want to store only k, which is 8, only store 8, then that means if it's less than or equal to, actually we just keep pushing. Yeah, I don't need this, so we just keep pushing, right? So we'll heap push, and then at any point if heap q, or if min heap, length of the min heap is greater than k, then we have to heap q dot heap pop that number, which we have to pop min heap. And also heap pushing requires min heap as the first parameter. And at this point, then is there a follow-up to this question? Oh my god, there is another one. Holy freak. Okay, and then at this point, I think by the time we traverse through all of this, we can simply just return. Is this not the solution? What if we say return the second smallest element? Wait a minute. Return the second smallest. Hold on. So let's just go through an example. Let's just say it's like 1, 2, 3, 4, 5. And we say, give me the second smallest element, which is this one. Which means we need to maintain a heap of size 5 minus k, right? Plus 1. Because we actually need to store this heap to be... The thing is, like, if k is equal to 1, because if k is equal to 1, right? This is saying give me the first smallest element, which means it's just give me 1. So if k is equal to 1, we can just simply return 1. Wait, hold on. What am I doing? Why do I even need to store anything? What is this code about? It's just the code a solution. Can you solve this problem with a constant memory? Yeah, actually, I don't even know if we need to. Why do we even need to? Why can't we just traverse through this? Because we go through 159, right? 10, 11, 13. I don't understand why we can't just traverse through it. Hold on. I think I'm overcooking here. Why can't we just literally go through, go until K numbers, right? Because we can go from left to right, top to bottom, right? So while, so for I in range from the length of matrix, and then for J in range from the length of matrix of 0, K minus equals 1, right? And if at any point, if K is equal to 0, we can just return matrix of IJ. Is that not wrong? Like, for example, right, if we go through this example, we go through 1. Well, we'll start at 1, the 0, 0, right? We say K minus equals 1. So now it's 7, right? We skip. Then it's 6. Then it's 5. Then it's 4. Then it's 3. Then it's 2. Then it's 1. Then it's 0. Then boom. Wait a minute. Oh my, wait. It's not in order. Hold on. Okay, this problem is not as easy as I thought. What's up with the Mexico filter? It's a good question. It's just to preserve my mental sanity. Wait a minute, this question is not as easy as I thought. Where the rows and columns are sorted in ascending order. Is this a typo? Because this says 10, 11, 13. Then it's 12, 13, 15. I don't even know what this means though. All the rows and columns of matrix are guaranteed to be sorted in non-decreasing order. 10, 11, 13, 12, 13, 15. What the hell? No, then my heap solution is still valid then, right? I think my heap solution is still valid. I can use a heap? Yeah, that's what I initially thought of. I thought for some reason I could just traverse linearly, but nah, I can just use a heap. But the thing is, the heap is not... So the heap size needs to be... technically, the smaller the K, the larger the heap needs to be. Because if we want to get the last number, the heap ends up being size 1, right? So the formula becomes... We have 9 elements, and if it says to get the 9th, then we just do 9 minus 9 plus 1, right? So, for example, if it says give me the second smallest element, which is this one, this means that the heap has to be of size this, right? This heap needs to store all of this, I believe. Or can we just make it so that the heap is like this? Well, it doesn't really matter. I think I can either choose to opt for a min heap or a max heap, but in both cases, like, depending on the input, it's both going to be, you know, have like a worst case. So in this case, we say it's the length of matrix. And then minus K plus 1. This is the formula, right? If this is our max size. So if our heap is of this size, we need to pop. So length of matrix. Length of matrix. Wait a minute. Can I even get the length of matrix? It's actually length of matrix times the length of matrix of 0 minus k plus 1. It's a little confusing of a formula, I feel like. So wouldn't this work? And then we can just simply return min heap of 0. Yeah. It works. Heap extend item will add all the items in the heap and then you can continuously pop. I've never, actually, I don't know if I've heard of extend. Maybe I've seen it once. What does heap.extend do in Python? Isn't actually a heap specific method. It's just calling the list method because heap queue works on, oh, I see. Oh, I mean, I don't know if you would use extend, to be honest. I don't know. I guess you can, but I doubt I would see an extend being used in like an optimal solution. I could be wrong. I could be wrong. I mean, I did technically get to a solution without having to look at an answer, and it's a list to flatten, list method to add like flatten. Yeah, I think I get it. You're just basically appending to an array, I think. It's basically what an extend does, it seems like. But I don't know if this is really relevant to the problem, or I'm struggling to see the relevance. I mean, this solution basically guarantees, well, it doesn't guarantee actually, it still would be n squared size of the heap if k is equal to 1. That would be, this would, I guess, kind of be like a trade-off maybe. But on average, you know, average time or average space, this would really just take up the size of, I guess it's based on this formula, n squared minus k plus 1. N squared minus k basically, which I don't know if it's that much better. I feel like it's not even that great of a solution. It's interesting to talk about, I guess. Is there any other solution I guess I could think of that has better than O of n squared memory? The time is O n log k. No, it's not. The time is, no, the time is still n by n. At least the one I wrote, because we do not leave early. We still have to process everything in the list. So that is not true. So technically this min heap solution is n by n, which I guess I could have just said n length of matrix squared, because we know that it's a square always. Minus k plus 1. So the thing is that this matrix is claiming to be sorted. So it's 1, 5, 9, 10, 11, 13, 12, 13. I don't understand how this is sorted. I don't know if this is a typo. but this to me doesn't look sorted. I don't know. I could be wrong. Maybe it's sorted from top down, but not necessarily left to right. This is an interesting problem to ask. I feel like it's actually not a bad problem. And is the kth smallest element in the sorted order not the kth distinct element? Yes, that makes sense. Okay, the follow-up is, could you solve this problem with a constant memory? So, using no heap, O of n, O of 1 memory complexity, O of 1. So that means, is there a way to solve this without having to kth smallest element in the sorted order? A memory complexity better than O of n squared. O of n squared. A memory solution better than, I don't even know if my solution is technically the naive solution, but how am I supposed to know what element? I feel like there's a trick to know what position it is based on the sort. I don't even know, because we still have to go through everything, right? But how can you? I guess you could just modify the existing array. I don't know. Whatever, let's see the answer. Maybe it's some jank. Some weird catch. Wait a minute, there's no cracking the fang video for this? There's no way. There's no cracking the fang. Oh, Leetcode.
Hey everyone, welcome back.
Thank you, Leetcode.
Back, and let's write some more Leetcode today. So today let's solve the problem kth largest element in an array. So we're given an integer array number.
This is not the problem. It's over. No. Kth smallest element in a sorted matrix. No, this is not right. What is this website? It scammed me. Alright, let's watch someone, I guess. I don't know.
Welcome to July's Leetcode Challenge. Today's problem is kth smallest element in a sorted matrix.
Why is there a decent amount of dislikes on this?
Hello guys, welcome back to TechDose, and in this video we will see the kth smallest element in a sorted matrix, which is from Leetcode number 378, and it is based on a searching algorithm. Let us now look at the problem statement. In this problem, given an n by n matrix where each of the rows and columns are sorted in ascending order, return the kth smallest element in the matrix. Note that they are asking about the kth smallest element in the sorted order and not about the kth distinct element. So you must find a solution which has a memory complexity of better than order of n square. So let's take an example for better understanding. In our case, we are given a row wise and column wise sorted matrix in non-decreasing order, and the matrix size is n by n. Our goal is to find the kth smallest element. Let's consider a one-dimensional matrix. It is not an n by n matrix, but I'm just giving you an example that if you have a single dimensional array, then in this case, if they are asking about the third smallest element,
I see. So it's sorted in ascending based on just the row and the column. Interesting. Okay.
and it will be 2 and not 3, because they are not talking about the distinct element. They are talking about even if you have duplicates, you can count them. Okay. Now, if you have an n by n matrix like we have on the right hand side, you see we have taken 4 by 4 matrix. Every row is sorted in ascending order, and every column is also sorted in ascending order. You see. Therefore, in this case, if you have to find the kth smallest element, and let's find out the fourth smallest element, what you can do is you can convert this two-dimensional matrix into one-dimensional array and simply get all the elements sorted, and you can find out the fourth smallest element. And in this case, if you enumerate everything in a non-decreasing order, then the fourth element will be whatever fits at index 3. So that will be 2 in our case. Okay. Now, one technique can be to just flatten this entire matrix into a single dimensional array and apply the sorting algorithm, which will be n square log of n square. But a better technique would be to just push all the first elements into a heap and then pop out the element which is the minimum out of this, and then push the next element of that row. This technique was already explained in the sliding window maximum problem.
Wait, oh, so you do a heap for each. You do a heap for each column?
You can follow this. The video link will be in the I button, or you can check out the description as well. This can be solved using heap, and the rank complexity will be n square log n, and the space complexity will be n square. But this is not the best approach in this case. This is just one of the approaches. Now, in this case, we can observe that since we already know that all the rows are sorted in non-decreasing order, all the columns are also sorted in non-decreasing order. Therefore, whatever will be our answer will be in the range of the smallest and the largest one. In this case, the smallest one is 1 and the largest number is 11. So our answer cannot lie below 1 or beyond 11, right? Therefore, the kth smallest element must be within the range of 1 to 11, and it must definitely be present in the matrix. Therefore, what we can do is we can search in our answer range. Okay, we know the range of answer. So the minimum possible answer, you can say this is lowest possible answer is 1 and the highest possible answer is 11. So if you want to search in this answer range, then one approach we can take is to take n pointers, and simply we can apply each of the pointer to the first element, just like we did in the heap previously. It is a similar approach, but this is kind of a more simpler one. In this case, you just compare all the n pointers, like you can take p, q, r, s, and you compare all these pointers p, q, r, s, and see which one is smaller. Whichever is smaller, you just have a counter. So you can have a count value c equals to 0. Now when you skip this, you move it to the right and the count will increase by 1. Again, compare 2, 2, 5, 7. Whichever is smaller, you just skip there. You could have skipped the second 2 as well. When two values are same, you can skip any one.
I feel like his explanation is not, it's not sticking with me. Alright, min-heap approach. Okay. The intuition for this approach is really simple if you think about it. So we treat row of column, however, before we get to okay, this is not the solution I came up with, I think. Binary search. I was thinking about binary search, but I don't know how we could apply it. Is that the O of 1 time? Or O of, yeah, O of 1 space? It took 2 days for me to figure out the approach. How does someone come up with the binary search? Yeah. Hard. Let's see. Okay, let's read through this, I guess. Or is there a... Bruh. Super easy for beginners. Yeah, it's O of n squared. This would probably not pass on a meta interview. Okay. We know that the rows are sorted and so are the columns. So we can treat each row or column as a sorted list in itself, correct? And the problem just boils down to finding the kth smallest element from amongst these n sorted lists. However, before we get to this problem, let's talk about a simpler version of the problem we find. Since all we need are a pair of pointers. Oh, I think maybe that makes sense. At each step, we check which element is smaller. Grass, if you think about it, we just need to run the algorithm for merging two sorted lists without actually merging them. Yeah. We check both elements, see which one is smaller. 2 is smaller. once we move pointer 1 step forward. Since we found our first smallest element, we decrement the count k, and we keep doing this until we find our kth element. Let's say if we wanted to find our fifth smallest element, we'll select 4 elements in order 2, 3, 4, 5. Now the pointers point at 10, 10, and 8 respectively. The next element we will choose is 8, the fifth smallest. Now that was simple enough to do. In this particular problem, we have n sorted lists instead of just 2. That's what adds to the complexity. Can't really keep n different pointers now, can we? The heap data structure is perfect for this problem since at all times we want to maintain n different variables, which each of them pointing to an element. I want to find the minimum amongst these n pointers. We just need to perform this operation k times to get our kth. So we need the min of n k rows essentially. For our implementation, we'll be considering each row an individual list. Since the columns are sorted, we can easily treat each column as an individual list. We'll take the first element of min n k rows, where n represents the number of rows, and add each element to the heaps. It's important to know what row and column an element belongs to. Without knowing that, we won't be able to move forward. So apart from adding an element to the heap, we also need to add its rows and column number. Hence our min heap will contain a triplet of information. Value row column. The heap will be arranged on the basis of the values. Also remember that each node contains a triplet of information. Value, row number, and the column. This will be used to move forward the corresponding row. Remember that even though a heap is implemented using an array, it's a tree-based data structure. We have a well-defined relationship between a node and all its descendants. 1, 5, 6. At this point, our k heap contains min k and k elements. Now we start a loop that goes until we iterate over k elements. At each step, we remove the minimum element from the heap. The element will tell us which row should be further consumed. Now we start a loop that goes until we iterate over k elements. We perform 2 operations in each iteration. The heapify operation maintains the min heapiness of the heap. The new minimum element now is 5. Add a new element. Keep on iterating till we exhaust k elements. Don't understand. The heap construction takes over x time. Pairing our min heap, min of k to n. Heap append the matrix r and 0. Heapify our list. This is cringe as frick. No one's reading this paper. That is crazy. No way people care that much about algorithms. Okay, you know what? Let's talk with ChatGPT, our friend. Can you explain the min heap solution? Here's the classic min heap approach. The matrix is sorted row-wise and column-wise. If you look at each row as a sorted list, the whole problem becomes find the kth smallest across n sorted lists. Yes, I get that. That's exactly what a k-way merge with a min heap does. Create a min heap of triples. Value row column. Seed the heap with the first element of each row. Okay. If n is greater than k, then you only need the first k rows. Oh, I think I get it. Seed the heap with the first element. If n is greater than k, you only need the first k rows. Repeat k minus 1 times, pop the smallest from the heap. Each row is sorted. Why is it n? If n is greater than k, you only need the first k rows. Seeding more rows can't help you before the kth pop. I don't understand that. I guess I'll find out what role he would have played. That would have been Aaron Yeager. That's for sure. Okay, so interesting. I think... Of course, that would have been Aaron Yeager. Who do you think you're talking to right now? And then, let's say it's 2, 3, 4. And let's say 3, 4, 5. Let's say k is equal to 5. So I think that the purpose of this algorithm is we actually build our heap. So it's clever, I guess. So basically, I think what it's saying is a random titan. No, Techno, that is you. You would be a random titan. So basically, what we're saying is that I think we initialize our heap to have 1, 2, 3, which is basically the first element from each thing. We pop the smallest one, right? Which we pop this, and k is equal to 4. Then we move our pointer here, I guess. Somehow we'd know. Oh, because we store the row in the column. So based on the row and the column, we just do row, the column plus 1. So then we would know to add another 2. So then the new one would be 2, 2, 3. If there's a next element, then we push. Otherwise, what? After k minus 1 pops, the top of the heap is the smallest. You never need to push elements down a column because the row expansion already respects the global ordering due to a row column sorting. Heap size is min of n or k. The new repost button. I think I've seen that. I think that's true. If the matrix isn't a square, the same idea works. No visited set is needed because you only ever push rightward. That's true if k is very large. Interesting. So this is saying the k is Good night, Hazel. Thank you. Appreciate it. I'm probably gonna end soon, but yeah, I just want to kind of understand this problem before I go to bed. But yeah, it seems like we're just adding, but I don't understand this part. I think, can you explain the min in more detail? There's a limit to how many rows we need to initially seed. Why not just do the range of n? You could push the first elements of every row into the heap at the start. That would work, but it can always work if n is much larger than k. The heap is acting like a k-way merge. If we want the kth smallest element, we can't possibly pop more than k elements. If we had 1,000 rows and we just want the 5th smallest element, then we'll start with 1,000 elements in the heap. Oh. Oh, that makes sense. Because vertically speaking, we can't even go past. If we had 1,000 rows, but we only want the 5th smallest element, of course we'd only want to have 5. So whichever is smaller, right? And you can also have 5 rows, or a k is equal to 100. Huh. I feel like that intuition is not that intuitive. And still get the correct answer. So it's saying, give me the first element. So for example, I guess if k was equal to 1, just give me the first smallest element. Your heap actually only needs to be as big as this. If k was equal to 2, then I guess also our heap only needs to be of size 2. So we'd only hold 1 and 2. So it's the min of n or k. Whether that's intuitive or not crazy intuitive, but interesting. Dang, summer vacation. I can't remember the last time summer vacation was a thing. Yeah, okay, I guess that makes sense. I'll sleep on that information, but it makes sense. And we just pop k minus 1 times. And yeah, you you keep pushing to the heap, I guess. Anytime. If there's more we need to add, go to the next one. That's pretty cool use of a heap that I never thought you could really do. That's cool. Alright, chat. I'm gonna call it. So hope you guys enjoyed the stream. I'll see you guys next time. Maybe tomorrow. See how I'm feeling. And take care, everyone.